release group in bacteria rhodopsin was somewhat in disagreement with what many people were feeling at that point. However, now that we have these spectra, we know that this is not due to a deprotonated arginine, but rather to formation of an arginine with a hydroxide bound to it. And this means that we're actually returning to a picture of the proton release group, which we first published. This is probably my most cited paper with Gobind in 1988, in which we drew the structure of M as having a hydroxide bound to arginine 82 and serving as the proton release group, this water molecule that was present in the L state, losing a proton to form this arginine hydroxide. This picture now actually corresponds more closely with what most people say based on X-ray crystal structures in cryo-electron microscopy. However, it's important to point out that although most people say that there are other groups involved in this, it seems that based on bands that you can see in the infrared, almost all of the proton occupancy change must reside within these two molecules, the arginine side chain plus the hydroxide. Well, anyway, we want to look a little bit now at the other protein, membrane protein that Gobind looked at was rhodopsin. And again, there is a highly conserved arginine, arginine 135, which changes its structure greatly upon formation of meta-rhodopsin 2. And without transducin, it was shown by this crystal structure from Klaus-Peter Hoffmann's group in 2011 that the arginine is quite close to a tyrosine. One of the nitrogens is within 2.7 angstrom of this tyrosine. What's most interesting that isn't often pointed out is if you look at the environment near here, it's almost hydrocarbon-like. Within 5 angstroms of this oxygen and this nitrogen, there is essentially nothing but hydrocarbon with the one exception of a methionine side chain. While this structure was able to discern numerous water molecules, several dozen in the crystal structure, none of them are within 5 angstroms of this tyrosine arginine H bond. In fact, the only other group that might serve within 5 angstroms as a possible H bond donor or acceptor from arginine is another tyrosine, which is slightly farther away. The interesting thing is that the distance between this tyrosine and arginine was perceived to increase in the crystal structure when the C-terminal tail of transducin was co-crystallized. And in this molecule, there's a carboxylate group which can serve as a counterion for that arginine and tyrosine. In this state, however, there is no obvious counterion other than perhaps the tyrosine. So the big question is, what is the structure of that arginine-tyrosine group? There's 3 general possibilities that you can imagine for sort of canonical representations of an arginine-tyrosine interaction inside a membrane protein. One is this first one where both are protonated and there is an external or a different counterion that is also present. And this is the one that looks like is probably present when you have the transducin C-terminus there, where the X minus here is the carboxyl group of the transducin. The other 2 are essentially the same charge, and they would be expected to be in rapid equilibrium with a proton moving back and forth between the arginine side chain, nitrogen, and the oxygen on the tyrosine. This is a sort of canonical, highly polarizable H bond, since these 2 are both have high proton affinities. These 2 structures are what we call the proton limiting structures for what we have nicknamed a Berry motif, and we use this abbreviation to stand for H bonded with a capital B, uncharged for the overall uncharged state, although in one portion of it it's a zwitterion, arginine and tyrosine. So the question is, can we model this at all? And in fact, computations that we did, these are density functional theory computations, indicated that if you actually put an uncharged guanidine near a phenol, that the hydrogen bond strength would actually be this huge value of minus 70 kilojoules per mole. Most of you who are biochemists may remember that an amide to carbonyl hydrogen bond in a typical alpha helix usually has numbers associated with that H bond strength of about negative 10 kilojoules per mole. So this is actually gigantic, much larger than any of the H bonds that are present in base pairing in DNA. Now, for the dodecyl-linked version of the same grouping at right, the computation decreased to negative 20 kilojoules per mole. But we have synthesized, Andrew Benico synthesized versions of both of these, and so I can now show you some experimental results that test whether or not these are present. So the first thing is these are actual measured crystal structures of the dodecyl-linked phenol and guanidine. And this shows very clearly that you, instead of making that folded up structure, which we sort of hoped we would get, that internal H-bonded version, we form head to tail dimers. And the shortest H-bond distance here is between the nitrogen of one guanidine to on the neighboring molecule, the oxygen, and this distance is 2.7 angstroms, 2.75. This is pretty close to what was seen in the meta-rhodopsin 2 structure on the last slide. Now, when you have a shorter linker, this ethyl linker results in an S-cis bond, which is a slightly higher energy than the all S-trans form seen with the dodecyl linker. We think that this higher energy is tolerated and is made up for by having a stacking interaction between the nearby phenol groups, plus also putting the oxygen of this oxyanion at that sweet spot that I told you about, where it can hydrogen bond to two NH groups of the guanidine. This structure can be compared with the HBr salt, which, unlike the other two, can crystallize without any methanol. So far, we've only been able to co-crystallize with methanol, and what this means is that these structures actually don't show the maximum H bonding strength that is present in very nonpolar solvents. So in aprotic solvents, the best way to see this, that you actually form the same kinds of dimer structures, is by looking at the UV signal from the phenol group. So if you will turn your attention to these comparisons of spectra in DMSO and in methanol. So I'm going to show you a row of changes as you add guanidine groups to this paracresol molecule. So first of all, these are extinction coefficient spectra. So even though the concentration has gone up by a factor of 10 between the black and the red, the spectral band shape has remained the same. Now when we start adding dodecyl guanidine free base to this in these solvents, in methanol, you see the formation of deprotonated cresol. And this is much the same spectrum that you would see if you were titrating this with sodium methoxide. This band at 296 is a well-known characteristic band of phenolate. In DMSO, there's a somewhat different absorption maximum. And I'm going to show you a little later on the concentration dependence of this equilibrium of this indicates that this is not a proton transfer in the traditional Brunstad-Lowry sense. This is a Brunstad-Lowry proton transfer in the protic solvent methanol, but here what we're doing is we're making a Lewis acid-base complex. And you can see this most clearly by looking at the concentration dependence of the spectrum of this molecule. This is the one that I showed you a crystal structure on the last slide. This is the free base of guanidine attached covalently to a phenol. And at very low concentration, this phenol is completely neutral. There's no sign of any ionization. And as you increase the concentration, you form this band at 318 nanometers. I haven't included spectra at higher concentrations than 10 millimolar, but if you go up to 200 millimolar, this 318 nanometer band eventually reaches almost equal in size to these bands to the band at 282. In contrast, in methanol, there's very little concentration dependence of the relative size of the protonated and deprotonated forms of the cresol. And this is classic Brunstad-Lowry behavior for a zwitterion. There's essentially buffering at the midpoint of the pKa's of the two groups. And we see similar things for the dodecyl-linked group. And the fact that the shape changes with the longer one, the deprotonated form is less favored for the long chain linker. That's a sign that the perturbation of the two pKa's on each other is smaller with a longer linker. Just as in amino acids, when you bring the amino group of an amino acid close to the carboxyl group, it tends to push their pKa's apart. The same phenomenon occurs in this case. You have pKa's pushed apart, and that results in favoring of the deprotonation of the phenol group here. Well, this effect is even stronger when you go to a less polar solvent. A completely nonpolar solvent of hexane is shown in here, and in this case you can see the band is at a little over, is also at around 315 nanometer, and these spectral changes occur over a range from just 0.06 millimolar up to 0.75 millimolar. These spectra are measured by taking solutions, 1 millimolar solution of cresol in hexane and about a 1 millimolar solution of dodecyl guanidine freebase in hexane. When you mix them together at room temperature, they crash out of solution as crystals. And those are one-to-one crystals. You can take them, no matter what your starting stoichiometry is, those crystals have a one-to-one stoichiometry as measured by redissolving them in DMSO and looking at their proton NMR signal sizes. But if you take those crystals and redissolve them in hexane at higher temperature, around 45 degrees, you get these spectra that are shown here. Now let me go over this real quick. This black spectrum here is a measured spectrum of pure cresol in hexane. It's just sharpened, it's the same as we saw in DMSO and methanol, just sharpened up vibronically. All the other spectra shown, all the other colored spectra here represent one-to-one mixtures of cresol plus dodecyl guanidine that are made by redissolving those crystals in hexane. And if you look at the intensity of this band at around 315 nanometer and plot it as a function of concentration, this is on a log-log scale, instead of increasing linearly with the concentration, it goes up as the second power. At low concentrations, the slope of this line is 2 on a log-log scale. And that's a sure sign that you're forming an equilibrium between two different molecules. You can also see this equilibrium shift by adding heat. So as you change the temperature, the lowest temperature is the highest spectrum here. As you raise the temperature, you tend to reduce the size of this peak. This is fully reversible. You can not really see it too well, but each one of these lines here of a different color is actually the superposition of two spectra measured first going up in temperature and then back down. And by fitting these using principal components analysis, we can figure out that the spectrum of the other component besides the black one is what's shown in red here. And this is not purely a deprotonated cresol spectrum. This is actually still a mixture of both proton transferred from the cresol to the guanidine and the other structure that I showed where the cresol retains the proton. So again, this structure represents the H-bonded structure that I showed previously. Yeah, okay. So the H-bond enthalpy is so strongly dependent in the polar DMSO solvent. It's only minus 11 kilojoules per mole, but using the Van 't Hoff plot here, we get a value of minus 74 kilojoules per mole, which matches the computed value. So there's also results that show that the proton NMR structure and other slides that I won't have time to show you have this interesting property that this really strong H bond results in very strange behavior for the proton NMR signals. So this shows the equilibrium that I showed you before, the formation of this dimer of the phenol with guanidine attached to it with an ethyl linker. And this equilibrium has a midpoint at a little over 100 millimolar. So measuring the NMR spectrum there, at low concentrations, the NMR signal from these guanidines is where I showed you before. It's very close to 4. As you go to the highest concentrations, it starts to approach the NMR signal from for the protonated dodecyl guanidine bromide. Meanwhile, although it reaches almost 2/3 of the way to that at about 100 millimolar, the change in the paracresol signal goes only a fraction of the way towards its values in the potassium cresolate salt. What this means is that you can't rely on NMR to tell you reliably when these groups are protonated, not nearly as reliably as you can by using optical spectroscopy such as UV or IR. When the H-bonded dimer forms in an aprotic solvent environment, both the guanidine and the phenol look mostly protonated by NMR, even though they are sharing one proton between them, and overall the pair has been deprotonated. So getting back to here, in this structure, we speculate that this very strong H-bond between tyrosine and arginine plays an important role in the activation of G-protein-coupled receptors. There's an energetic problem which people may not realize of having a buried arginine in such a nonpolar region of the protein. The problem isn't necessarily so apparent when you think about this reaction starting from rhodopsin, because you're adding the energy of a photon, and you might imagine, well, you could end up with quite an energetic state at this point. But you also have to remember that this reaction goes also in the reverse direction here. Metarhodopsin 2 with a G-protein tail has that tail being removed. The counterion of this C-terminus is being removed, leaving a naked positive charge, if that's what it is, in that very nonpolar binding site. And the best explanation for how that can happen is if this C-terminal tail pulls a proton with it, leaving this H-bonded uncharged arginine tyrosine that has a very strong negative 70 kilojoule per mole H-bond between it. And so these are just quickly the conclusions. The arginine side chain binds hydroxide very tightly. The only accurate way to model the fully deprotonated arginine side chain is in aprotic solvent, free of water and hydroxide. All prior measurements of arginine titrations in water showing a pKa of 14 have actually measured a hydroxide binding constant corresponding to a dissociation constant of hydroxide of about 200 millimolar. And in hydrocarbon-like environments, a phenolic group can form an extremely strong H-bond to deprotonated guanidine with a formation enthalpy as large as minus 70 kilojoules per mole. This could hypothetically occur in membrane proteins as this Berry group that we define. And detecting this group in proteins should probably not rely on NMR, which can give this deceptive and anomalous result where both groups simultaneously seem protonated even though one proton has been removed from them. The rapidly exchanging shared proton might appear to have an occupancy of greater than 80% on both guanidine and phenol simultaneously. Thank you for your attention. Oh, and I just want to put some acknowledgements up there. Thank you.
Thanks very much, Mark. Is this on? Yeah. Thanks very much. That was a very, very detailed biophysical talk. Very nice. It's good that we have a broad range of subject here. We are running a little bit late. Is there any, maybe one question? Has anyone got? Can I just ask a question that occurred to me? Because how general is it? I mean, you must have have you looked in crystal structures where this sort of constellation of tyrosine, arginine occurs? I mean, is it very unusual? Or
so there's an atlas of crystal structures that was first published in the early 1990s. And at that time, there were a few that seemed to have this constellation of possibly a linear arrangement of arginine with tyrosine. And they've gotten a little bit more common in that sampling of crystal structures, which is now online and is updated regularly.
Okay.
So there does seem to be, so they cataloged all the pairwise interactions between different pairs of amino acids. And for arginine and tyrosine, there's about 5 or 10% of the arginine tyrosine close interactions within, say, 5 angstroms of each other. About 5 to 10% of them seem to have this kind of.
And does it have a special role in biology? I mean, do they always have this sort of, because it's such high energy, that they have a specific role in each case?
Well, I did not go through the entire database and look at all of the examples. The crystal structures of the GPCRs that have been solved do show conserved, but not necessarily with this close a distance for this H bond of 2.7 angstrom. This is shown most clearly with the meta-rhodopsin 2. Again, we are speculating, we're hypothesizing that this does play, in the case of GPCRs, a key role in terms of being able to form this very stable group which can attract into the interior of the membrane the C-terminal tail, which is an acid group. So buried inside the membrane, this arginine tyrosine, if it's neutral, still has the quality of being very basic. And so this would explain how the C-terminal tail of it would help to explain why the C-terminal tail of transducin is so attracted to that point, but also how it can then be released without violating free energy principles.
That's really interesting. Thank you very much. I think we need to move on now. And please join me to thank Mark again for his wonderful insight.
Thank you.
So we come to our last speaker. Let me just quickly get my notes. This is Professor Yotaro Takagaki, is that right? He got his PhD in biological chemistry in 1975 at the Faculty of Agriculture, University of Tokyo. He was a postdoc at the National Institute of Genetics in Japan with Hirota. Then he did his second postdoc in Gobin's lab between 1976 and 1982. Moved then to the MIT Center for Cancer Research, where he was staff scientist, went back to Japan in 1990, where he worked first at the Mitsubishi Kasai Institute of Life Sciences in molecular immunology, and then at Kitasago University Medical School, where he was a professor, and then between 2005 and 2010 he was at the Tokyo Women's Medical University and is now visiting professor at Nikon Pharmaceutical University since 1913. And the title of his talk, Gobin in the History of Protein Sequencing. Please, Professor.
Thank you very much for kind. Thank you very much for kind introduction. I'm sorry, a lot of difficult Japanese names. It's already 40 years, more than 40 years since I joined Gobin's laboratory, so it's a very old story. I'm basically retired after this job and writing reviews and that sort of things. I volunteered to talk in tomorrow's session, but found myself in the main lecture, and I was surprised, but I went back to my old notebooks and tried to find things to talk, and so it was, I hope I could give students here some of the message that I want to convey. Okay. Gobin, in his difficult time, he said in a movie previously, around 1951, he actually produced a paper for stepwise peptide sequencing from N-terminal. It's a thioacylation method. Edman came out with isothiocyanates in 1950s, and 1 year after Gobin's thioacylation method came out. This had an advantage of producing free amino acids. And so some people did. Okay. Thank you very much. Okay, thank you very much. So, some people took, like, there's a book concerning advanced method in protein sequencing. Russell Doolittle of UC San Diego used this thioacylation method until this time. In this book, he mentions Kenner and Corona paper. This is 1952. And then he describes in this chapter how he modified thioacylation method. But anyway, his Gobin's sequencing method persisted quite until recently. Although Edman had an advantage these days because of high sensitivity of HPLC. HPLC made possible the Edman degradation below sub-picomolar level sequencing. So Edman degradation has been a major method, but Gobin's method still persisted and quite a long time. He also published paper concerning stepwise peptide sequencing from C-terminus using carbodiamides. And there were other chemical reactions too, but the chemical reaction has a drawback. If you meet with proline, then sometimes sequencing gets blocked, etc. And then there are much easier method of carboxypeptidase method, sequencing from C-terminus now. So this didn't take on, but Gobin, in his beginning of independent career, had desire to get into proteins. So when I joined in 1976, actually, this is Yuki Hirota, my boss for my first postdoc. He discovered DNA polymerase 2 and 3s. He told me that you should associate yourself with great person for your scientific development, and he was very helpful in squeezing me into Gobin's laboratory. This is Marcia Rosner when she was young, and then this is Mike Ryan. Marcia is still young. Sorry. The last person to work with tRNA synthesis function, he was pursuing function. But when I joined, Gobin told me that in 1968, in International Biochemical Society in Japan, I said to people, I'm going to synthesize a functional protein in vitro, in glass tubes. And most people, almost all people said, you are crazy. You are stepping into the region of God's area. And he smiled, but I've done it. And then he told me, proteins are important. Membrane proteins are very difficult. So I'm going to work with membrane proteins. That's his attitude. It took me 6 years to complete what I had to do. At that time, he didn't take on thioacylation sequencing method. He actually used Edman degradation because Gerhard Garber He was a great guy. He's a nice person. He came from Canada, McMaster University. He sequenced elastin before coming to Govin's laboratory. So he's basically a protein sequencing person. And sorry about the quality